Hello everyone, I'm Arun Sankar. I'm a PhD scholar working with Professor Raghunathan Rangaswamy in the Department of Chemical Engineering, IIT Madras. I work in the area of droplet microfluidics and droplet millifluidics. In this video, I'll be talking about my experiments in droplet millifluidics. Droplet millifluidics deals with the generation and manipulation of drops inside channels having a characteristic length of the order of a millimeter. Conducting these millifluidic experiments requires fabrication of the millifluidic channel, generating droplets, and capturing the droplet motion using a camera. The fabrication of millifluidic channel is very simple and cheap. It does not require any complicated soft lithographic techniques, and it does not require a clean room facility, unlike that for microfabrication. Generally, these devices are fabricated using a transparent material so that the flow can be easily visualized. Since the size of the drop is of the order of a millimeter, we don't require a microscope to observe the drop. We just need a camera. Generating drops is the first step in any droplet micro or millifluidic experiment. The attractive feature of millifluidic or microfluidic way of droplet generation is that it can produce monodispersed drops, that is, drops of uniform size. The ability for periodic generation of monodispersed droplets has been exploited in many fields. Droplets are used as milli or micro reactors to carry out various chemical reactions. Certain monomers have been photopolymerized in millichannels to make uniform size polymer particles. This figure shows an experimental setup where certain monomers are photopolymerized inside a millifluidic channel. The fixed bed reactors and ion exchange columns require particles of the order of a millimeter. These can be synthesized in a millifluidic channel by suitable method. Now, I'll come to the fabrication of millifluidic device. We fabricate the device using a transparent soft material called PDMS or polydimethyl siloxane. The fabrication process can be divided into many steps. First, we have to make the mold of the device. We can prepare the design using a CAD software, and the design can be cut from a metallic sheet using laser cutter. Now, we prepare a mixture of PDMS and curing agent in the ratio 10:1. The weight of the mixture depends on the size of the channel. This mixture has to be degassed in a vacuum desiccator to remove all the dissolved gases. Now, after degassing, pour the PDMS and curing agent mixture on the mold. Cure or heat this in a hot air oven at 65 degrees for 45 minutes. During curing, the mixture will be solidified. Now, peel off the PDMS layer from the mold. This layer has to be sealed with another PDMS layer to get a leak-proof channel. Now, we take a clean glass slide and coat a thin layer of PDMS and curing agent mixture on the glass slide using a spin coater. After that, we have to treat the cured PDMS layer, which is peeled off from the mold, to plasma treatment. Plasma treatment helps to bond or stick the PDMS layer to another PDMS layer or glass to have a tight bond and thus a leak-proof channel. After plasma treatment, the cured PDMS layer has to be sealed with the glass slide coated with the thin layer of PDMS. Again, cure this sealed device in an oven at 65 degrees Celsius for 45 minutes. Then put inlet and outlet connections for the fluids to enter and leave. And now the device is ready to use. In this slide, you can see the images of different molds we use. The first one is for a T-junction droplet generator. and this one, the second one, is for a cross-junction droplet generator, and this is the mold of a cross-junction droplet generator and a diverging converging channel, and this is a mold for a diverging straight converging channel. And these are the images of final PDMS leak-proof channels. The first one on the left is a cross-junction droplet generator, and the continuous phase fluid enters through these inlets and discrete phase fluid enters through this inlet. This is the cross junction and this is the outlet. On the right side you can see a diverging straight converging millichannel. As I said earlier, generating droplets is the first step in any droplet micro or millifluidic experiment. And millifluidic way of droplet generation produces monodispersed droplets periodically. There are different geometries used for droplet generation. A T-junction droplet generator, a cross-junction droplet generator, a co-flow junction, and a flow-focusing junction are some of the geometries used for droplet generation. We have used a cross-junction droplet generator for our experiments. As you can see in the video, the droplets are generated at the junction in a periodic fashion, and the size of the drops are uniform. The size of the drop form depends on various quantities such as the flow rate of the continuous phase, the flow rate of the discrete phase, viscosity of the continuous phase, surface tension of the two fluids, etc. We saw how the drops are generated in a millichannel. We sent these equally spaced drops into a diverging converging millichannel, a 2D channel. In the first video, you can see the drops are well separated and so they are not interacting with each other. As the separation decreases, the drop starts to interact with each other and form some patterns in the diverging converging channel. As you can see in the video, when we reduce the interdroplet spacing in the inlet channel, the drops interact more and it forms a two-layer arrangement in the diverging converging channel. When we even reduce the interdroplet spacing in the inlet channel, it forms a three-layer arrangement. These observations are very similar to that of Jose and Kubot in microchannel. They also observed this layering of drops in microchannels. The experiments at two different scales indicate that the interactions between the drops at the two scales is similar, and the model developed in the group could capture this dominant interaction between the drops. To summarize, we have discussed about the advantages of millifluidic experiments, applications of droplet millifluidics, millifluidic device fabrication, the droplet generation, and about the interaction between the drops in a 2D channel. With this, I end this presentation and see you later with the interesting stuff.